everybody. In this class, we are going to be talking about electrical potential. And we are going to be going straight to the point. First thing here, we'll try to talk about electrical potential energy. Electrical potential energy. Now, to define or to explain electrical potential energy, we must first of all, explain the work done due to charge. Now, if we say here we have a charge Q, right? We say we have a charge here Q, and we have another charge here, small letter q, right? There must be work done. Are you getting it now? To bring this charge to this point. Let's call this place arrow A. Let's also say we have moved this charge to another distance, arrow B. There will still be another work done, right, to move this charge here. So let's say the work that was done to take this charge to this point is, let's call it U A, right? And the work that was done to take this charge to this point, we call it U B, right? So it means that the total work that is done in here, because first of all we move this charge, the charge was here before, right? Then we now move it to this point. So the total work that is done between these two given scenarios will be work done from A to point B, right? Which is the same thing as the difference between the energy here, as the work there, and the difference between the work here, UB. Are we getting it now? Yeah, so now let's talk more deeper into this. This work here, this UA, remember that energy is equal to work, and work is equal to force, right, times distance. So the work in here, the work needed here will be, remember that F is equal to QA. That's why foundation is very important. And this arrow here is arrow A, right? This arrow here is arrow A. So when we substitute in here, we have Q, we have QE, right? We have QE times arrow A, or QE arrow A. Same thing for this guy. This guy will be QE arrow B. So that when we substitute in here, we'll have QE arrow A minus QE arrow B, which is same thing as QE arrow A minus arrow B. If you want to express this as the difference between final minus initial, right, it's just simple math. All you need to do is to put minus in here, right, and the arrangement here will change. So this will now be arrow B minus arrow A. So we can see that electrical potential energy can be defined, write this down from this expression. Make sure you note these formulas down. Electrical potential energy now can be defined, are we getting it now, as the work that must be done to move a charge between 2 points within an electric field. Simple. Is the work that must be done to move a charge between 2 points. I mean electrical potential energy. Are we getting it now? Alright, so that means in general U is equal to the work that must be done. So let's say we have the W, this is the work that must be done, right? Then we want to integrate that work between 2 points. Let's call the first point arrow A and the second point arrow B. So remember that work dw is equal to, now remember work is equal to force F times distance. This distance now we take a small infinitesimal distance, right? Yes. And let's call it the arrow. Are we getting it? So we substitute, this become the arrow times F integrated over arrow A, arrow B. Are we getting it now? So we already know that F is equal to what? KQ over arrow square, is it not? So when we integrate this now, we integrate this arrow A and arrow B, and we have the arrow here. So remember that when we integrate, everything here is a constant. This becomes K, Q, right? The integrand of arrow B, arrow A, 1 over arrow square, the arrow. So when we integrate this, what do we have? We integrate integral of 1 over x square, the same thing as saying integrand of, right? And this same thing as saying x minus 2 plus 1 over minus 2 plus 1. So this gives you x raised to power minus 1 over minus 1, right? So that gives you minus x raised to power minus 1, or minus 1 over x. Knowing fully well, knowing this, let's apply this to this integral, right? So applying this to this integral, what we'll have here, applying this, we'll have k, q, right? So this place will now be minus 1 over arrow, but we still have our limit, right? Our limit is arrow B, arrow A. So using our upper and lower limit, this becomes K, Q, in the brackets of minus, right, 1 over arrow B minus 1 over arrow A. I'll get it now. So this is what we have, or that should be equal to K, Q, in the bracket of 1 minus arrow A minus 1 over arrow B. Alright, so this is what we just need to know, right? Another formula for electrical potential energy. But why do integral? Well, we can just evaluate with simple arithmetic. Why doing integral? We can just use normal arithmetic to evaluate this. Now let me show you the normal arithmetic method. Remember, right? Remember, we say that U is equal to F times arrow. We also know that F is equal to what? K, Q, is it not? Over arrow square, right? Now, times this arrow also will now be arrow, is it not? Yeah, so when they cancel out, you have K, Q over arrow. So when you have 2 points, point A and point B, you now have difference between 2 points, right? That will be K, Q, in the bracket 1 minus arrow B is so simple, is it not? Yes, because from here you have K, Q, Q. This 1 over arrow can be factored out as 1 over arrow. So if there are 2 arrow, you now subtract arrow 1 minus arrow 2. So if that is true, we can now go to the next section here where we talk about electrical potential. So we have been doing electrical energy since. Let's talk about electrical potential. But first of all, before we talk about electrical potential, we must understand we have been talking about electrical energy. Let's assume that we are not moving this point from point A to point B. We are moving it from infinity to a point, right? So if we move a charge Q from infinity to infinity, right, to a point in a field. So if we move a charge Q from infinity to a point in a field, infinity means any arbitrary distance. When we mean infinity in physics, sometimes we don't always mean a place that is very far. We just mean a generalized distance, a distance that we can refer to at any time, right? We don't know where it is, a point that was not defined before. So when we take a charge from infinity to a point in a field, that means that we'll have U. Remember the formula we derived before, that U is equals to K, Q, right? Q naught 1 over minus, right, arrow B 1 over arrow A. Is it not? Now let's say this arrow B now is the normal distance we are using. That is, this arrow B is this point. I will get it now. Yeah, so see that. Let's go. So let's say we have, remember that U is equals to K, Q, 1 arrow A minus 1 over arrow B. You know, sometimes I'm surprised, is this place arrow A or arrow B? Don't worry, it just depends on how you interpret it, right? Anyone here can be B, here can be A. Now listen very carefully. Let's say point B is a place of infinity. Point B is in infinity. While point A is the point in the field, right? Point A is the point in the field. So we can say arrow A, let's just generalize arrow A as arrow, and arrow B to be infinity. So when we substitute in here, we'll have U to be equals to K, Q, 1 over arrow minus 1 over infinity, is it not? And 1 over infinity is 0, right? So that means that we'll have U to be equals to K, Q, 1 over arrow. So in this point, this is the electrical potential energy from a point of infinity. Now, what is electrical potential? Electrical potential is defined, the symbol is V. Electrical potential is defined as this work done now, this electrical potential energy from infinity, this U, per charge. I get it now? That means V will now be equal to K, Q, 1 over arrow all over Q. So when they cancel out, you have K, Q over arrow. This is what we call electric potential. I'll get it now. Yeah, so you should understand that electrical potential is a scalar. Yes, it's a scalar quantity. So when a negative charge is what is producing the field, if a negative charge is producing the field, what will happen is that if a negative charge is producing the field, that means we will have V to be equal to minus, right, K Q over R for negative. And if it's a positive charge producing the field, we'll have K Q over R for positive. Are we together now? Yeah, so this class is just to explain the concept. In the next class, we'll be solving all the examples and we'll dive into the exercise. So first, the next thing we'll talk about here, make sure you mark those formula down because they are very, very important, right? Yes, those formulas are very, very important. You should also understand in here, so there's something that we need to understand. Since we have defined electric potential V is equal to U over Q, right? Now let's take a point charge. Let's say this U is W. We already know, right? So that means that we can say that V is equal to W over Q, or W is equal to QV. We'll be using this when we begin to solve problem. Make sure you know this. This is another formula to note. You don't need to memorize the derivation. Just understand this. Now, also W is equal to 1 over 2 mv squared for kinetic energy. That means that we can equate as 1 over 2 mv squared is equal to QV. This is another formula, right? Don't worry, we'll explain those things in detail. The next thing we are about talking is equipotential surface. Equipotential surface. What is an equipotential surface? Simple. An equipotential surface is a surface in which all the points have the same potential, have the same electric potential. Simple like that. If we have point A, let's say we have a cycle like this, right? We have another cycle like this, right? We have another cycle like this. Let's say this is point A, B, C. It means that the electrical potential in this region and the electrical potential in this region and the electrical potential in this region are equal. They are equal. The electrical potential in all the regions are equal. So if they are equal, what will happen? There will be no work done. Are you getting it now? There will be no work done. So if the electrical potential are equal, are we getting it now? So if a charge moves from this point to this point, since they are equal, let's say VA minus VB, what will happen? 0. So there is no potential difference. Are you getting it now? In an electrical, in an equipotential surface. Are you getting it now? There's no potential difference. Potential difference in an electrical equipotential surface is equal to 0. Are we there? We are there, right? Alright. So right in here, let's go deeper. You know, this is outside this course, but I want you guys to visualize this. Why do you think, right? Why do you think current do not electrocute birds flying on? Why do you think electric wire do not shock birds flying on a wire? Sorry, why do electric currents do not electrocute birds flying on a high tension wire? The reason is because the birds only fly on one line like this. Are we getting it now? Yes, the birds only fly on one line, and in this line, the potential difference, let's say this is wire A, this is wire B, and this is wire C. The potential difference here is VA. The potential here is VA, right? So there is no potential difference because it's just on one potential. I'll get it now. If peradventure that bed touches another wire, it mistakenly touch another wire, what will happen? There will be, this place will be VB, right? So the difference between VA and VB will create a potential difference, and that potential difference will allow current to flow in the body of this bed, and the bed will be electrocuted. But since the bed is just on one potential surface, even though it move, it's still on the same point. So there is no potential difference there that will shock the bed. Why do electric shock human being? When we touch the wire, no matter how we are connected, even if we are connected to a pole, right? That pole is connected to the ground, and that ground has another potential. It has a lower potential. So that potential of the ground, let's call it VG, and the potential of the wire we touch, even though you are on that pole, since that pole is connected to the ground, there will be a potential difference. Let's call this, let's say VA minus VG. And that VGA minus VG will cause current to flow in your body and you'll be electrocuted. Are you getting it now? Yes. Thank you very much. In the next class, I'm going to be going deep to be solving problems, and after that, we move to the next chapter, which is dielectric. God bless you.